Hi, my name is Alex Dixon. I'm an application engineer for Agilent Technologies, specializing in digitizers, like our new M9703A digitizer that you see here. This digitizer was designed specifically for high-speed, high-resolution, multi-channel measurements. The M9703 has 8 channels of DC-coupled inputs going into 12-bit analog-to-digital converters. This allows us to achieve unprecedented measurement fidelity and channel density for gigahertz speeds.
The key challenges for high-speed multi-channel measurements are to get simultaneously high sampling rate and bandwidth for measurement of fast signals, high resolution to obtain the best signal measurement quality, synchronous measurement across a large number of channels to achieve accurate time positioning or phase coherency across channels, and fast data transfer to a host controller to optimize measurement throughput. Let's see how the Agilent M9703A architecture and technology help solve these challenges. Agilent's M9703A digitizer is the industry's first 12-bit digitizer that complies with the AXIe open standard. AXIe is based on the industry's well-established advanced TCA, adding extensions for instrumentation and test. The AXIe consortium, including various manufacturers, provides an open standard that creates a robust ecosystem of components, products, and systems. This standard allows reaching unprecedented capabilities in modular instrumentation by providing 5 times more board size and 7 times the cooling capacity of PXIe. The usage of the AXIe standard for the Agilent M9703A drastically simplifies the creation of very dense data acquisition systems that include a large number of high-speed synchronous channels with wide dynamic range. When looking at the high-level block diagram of the Agilent M9703A, we can see the typical architecture of a high-speed digitizer, implementing fast analog-to-digital converters, digitizing the acquired signal, and sending the data to the acquisition and processing FPGAs. The FPGAs then store the data in the large DDR3 memories for a total of 4 gigabytes memory, or transfer them to the PCIe backplane bus with up to 2 gigabytes per second data transfer speed. In order to get the best bandwidth and resolution, the 4 analog front-end mezzanines implement a revolutionary design architecture, allowing a DC-coupled front end with up to 2 GHz instantaneous analog bandwidth and 12-bit resolution. The performance reached is outstanding, with typically 8.8 effective bits, 57 dB signal-to-noise ratio, and 60 dBc spurious-free dynamic range at 400 MHz signal frequency. At the speed reached by the Agilent M9703A, the quality of the clock signal is a critical point to get high measurement fidelity. A clock jitter of only 1 picosecond would degrade the effective resolution to a maximum of 8 bits for a 500 MHz signal. In our case, the digitizing clock is created in a very low-phase noise time-based mezzanine, implementing in-house chipsets, hitting an overall acquisition phase noise of 225 femtoseconds. The module implements a total of 5 Xilinx Vertex 6 FPGAs, 4 of them acquiring, processing, and transferring up to 6.4 gigabits of data per second. These FPGAs have been very carefully positioned on the board and have dedicated heat sinks in order to have very good airflow, which optimizes their cooling. Each FPGA is connected to a bank of up to 512 megasamples of memory. In addition, an optional VHDL development kit allows the implementation of custom real-time algorithms in the processing FPGAs. The VHDL development kit consists of a set of functional cores, a base digitizer design, a test bench environment, and the necessary tools for VHDL programming. In multi-channel measurements, it's often crucial to ensure excellent time resolution across all channels and minimize the skew between channels. Maximizing the number of channels in a single module enables excellent multi-channel measurements thanks to a shared clock. In this design, the time-based mezzanine uses a special chip developed in-house by Agilent engineers, allowing very accurate trigger-to-time resolution of less than 15 picoseconds typically. In some cases, the captured information needs to be transferred as fast as possible to the host controller for final processing and visualization. The AXIe architecture allows very fast data transfer thanks to a 4-lane PCI Express Generation 2 backplane bus. This high-speed backplane enables transfer at speeds up to a theoretical 2 gigabytes per second. Here, an Agilent M9703A MXG source is being used to provide a CW single-tone signal to 2 channels of the M9703A digitizer. The phase and amplitude differences occurring between 2 channels of the digitizer for a common input signal are measured. Our goal is to provide proof that the M9703A is not only a high-precision 12-bit digitizer with excellent dynamic range, but also an excellent choice for applications requiring phase-coherent sampling across many channels. An application run takes repetitive measurements of the difference in instantaneous phase and amplitude across 2 channels. The instantaneous measurements are added to a statistic population for calculating one standard deviation of both the amplitude and the phase differences. After a few seconds here, you see that the standard deviation of the channel-to-channel phase difference remains a fraction of 1 degree, and the amplitude differences between channels are also very stable over time. Each M9703A module takes up only 1 U of rack mount space inside an AXIe chassis. If more than 8 channels are needed for an application, multiple M9703A digitizers can be combined together with a shared clock distributed over the AXIe chassis backplane. This allows for configurations of 40+ channels in a synchronous acquisition set.
So as we've seen, Agilent's M9703A digitizer solves key challenges by simultaneously providing high sampling and bandwidth, high resolution, synchronous measurements over a large number of channels, and fast data transfer to the host controller. Thanks for watching.